Reservations in two-way slabs by means of yield lines. This video will deal with the cases 16 to 20, and it's about a slab who is on three sides fixed and on one side freely supported. The orange part is the freely supported edge, and the green part is where the slab is continuous or where the slab is fixed. This video will handle with case 16, which is a rectangular hole. This is a rectangular slab concrete fixed on three sides and freely supported on the fourth side. We first start with calculating the maximum bending moment without a reservation in the slab, so that we can compare afterwards what happens with the bearing capacity when we make a reservation in it. So for the slab without a reservation, we use the method of the yield lines, and for the negative bending moment on this side, we have a yield line. Same happens on the right-hand side and on the bottom. Then in the corner, we have the 45 or the 60-30 degree rule. So the yield line starts with the crosses of the rotation axis and goes into the slab. The same happens here below. It's 60 degrees and 30 degrees. There we have 2 times 45 degrees, and on the bottom also 2 times 45 degrees. And then we connect the two dots, and these are the yield lines for the slab without a reservation. You have some geometric characteristics, which is S1. And for S1, it is the cotangent rule, which means the base of the triangle S1 of the height of the triangle S1 is equal to the base of the triangle divided by the sum of the cotangents of the two adjacent corners. And we see that this is a over 2 square root of 3. For S2, because for S2 it is because this is 30 degrees, so you have that S2 is cotangent 30 degrees times S1, and is of course equal to a over 2. It's obvious because of the symmetry, and it will be a over 2. Then S3 on this side, again we use the cotangent rule and we find a over 2, and S4 is equal because this is 45 degrees, so S3 and S4 must be equal, so S4 is a over 2. So we have 2, 3, and 4 are a over 2, and S1 is a over 2 square root 3. Now let's have a closer look at the yield lines. For the negative bending moments, we have M1 and M2. You can calculate what is M1 regarding the positive bending moment. But the more easier way to do it is that because the reinforcement of the slab, the bottom reinforcement of the slab are most of the time equal. So you can easily state that M is equal to M1 is equal to M2. But if you want to do it otherwise, we can always give this a different bending moment. The slab will behave like it is reinforced. So if we say this, for instance, is 1.5 M, and it is also 1.5 M, then if you put the right reinforcement, that will look like that. So, but for ease of working, we take M1 equal to M2 equal to M. Then the S1, we know that S2 is 3 and S4 is A over 2, and S1 is this value. And now we will calculate the work done by the external forces. And this is summation of triangles and a summation of rectangles. For the triangles, we have S1 times A, then we've got 4 triangles here, and S3 times A, and the mean deflection of a triangle is delta over 3. What's left is this portion, which is B minus S1 minus S2 times A, and the mean deflection delta over 2. So we fill in the known parameters, and we have this equation. The work done by the internal forces are calculated by projecting the yield lines to their rotation axis. This yield line will be projected to the vertical axis of rotation, multiplied by the angle of rotation, which is delta over S1. So we have AM delta over S1. For S3, the same. We have this yield line, which is, of course, M2 times delta over S3. And for this one, we have M times A times delta over 3. Then we go to the yield line M1, which is B times M1 divided by S4, or we we have M times B divided by S4. And last but not least, we have this yield line projects to this x, which is B divided B times M divided by S2. We can fill in the different parameters, and then by looking by E is equal to D, we get M, and the bending moment of the slab without a reservation, we call it M0, is equal to this formula. Now let's check this formula for a square slab. Then A is equal to B, and M0 becomes this value, or you can write it as QA squared over 42, which corresponds well with the value quoted in literature. For the further calculations, we will use EX because it's easier to write, dx as V divided by delta M, and E equals D. From that on, we find that the bending moment is the load in ULS times EX divided by dE. Suppose an existing slab, so the reinforcement is there, AS0 is without the hole, AS is with the hole, but for an existing slab there's no hole, so those two are equal. The bending moment is the load times a factor depending on geometry. The maximum bending moment without a reservation follows a similar equation. And now we can easily say that when Q over Q0 is C0 over C is M0 over M. And then you see that we call this bearing capacity. It is the bearing capacity with reference to the bearing capacity of the initial slab without the hole. Or you can write it like that. Now for case 16, let's go deeper in on it. First of all, it has a two-way slab. It means that B must be between A and 2A. The horizontal position of this type of reservation is 1, or let's say D2 plus D4. So D2 plus D4. It means this side of the reservation. This side of it must be on the left-hand side of this field line. And this side of the reservation must be on the left-hand side of this field line. You do that because otherwise you have to split up all formulas and it gets very complicated. This only shows that for a certain type of reservation, we can construct formulas. Of course, D4 must be smaller than S1, that's for sure. And D4 must be smaller than S1 over S4 times D3. It means that this point is on the left-hand side of this yield line. And the vertical position, D1 plus D3 must be bigger than S4. So it means that this point of the reservation is below the horizontal yield line. and D3 is smaller than S4, so it means that this line of the reservation is above the horizontal yield line. These are just the limitations for the formulas that we will construct. You can fill in the different values of S, and now you have the conditions written as this. What does that mean visually? For instance, this reservation fulfills all those conditions. It is something like that. It can be like this. You see that this right-hand side is on the left-hand side of the yield lines, and those 2 points are all on the left of this. Be a reservation like this or this. So we can have different reservations with this with those conditions. Now, this is an example which is not okay because those 2 points are on the right, and also those 2 points are on the right of the yield line. So this is not a reservation covered by the formulas we are going to give in the next slides. Some more geometry. We can calculate S1 and S2, S3, and S4, like we've seen in the previous slides. The factor X1, it's the factor where the reservation, or where the whole of the reservation is cutting the yield line. X1 is not equal to D4. It looks like it, but it's not. So it's where X1 is where the yield line is crossed. Of course, this is angle of 60 degrees equal to D3 divided by X1, because it's this angle or this angle. Same for X2. It's where the reservation crosses the yield line, and Y1 is on the other side is equal to this. So we use the relations in a triangle, and we say that on a distance x, the total deflection delta x is equal or is proportional to the maximum deflection times the sector position divided by the original position. So bearing this in mind, we see that the deflection on this side, because the deflection here is delta, that's the maximum. Just remember, you need a mechanism of moving parts. So this is delta. From there to there, it's from 0 to delta. So what's this point here? So this point is then nothing else than using this formula, delta d3 over s4. That's the maximum deflection of this part of the slab regarding the highest deflection. This side is, of course, then the same as delta d4 divided by s1, and this is y1 divided by s2, because this is rotating about this action, this axis, so this is s2. This is rotating about this axis, so it's s1, and this is rotating about this action, so it's s4. So now we can easily calculate the work done by the external forces, and you see that for the orange parts, the rectangular parts, we will have like this one, d1 times d4 times the mean deflection. It's 1/2 of the maximum, and the maximum is d4 over s1. That's for this part. Then we go to this rectangle, and we have this element. And so we go on until we have all the orange elements. And then we add up the green parts, which is on this side a times 3 divided by delta over 3, which is the mean deflection. And then we have 4 elements. For instance, we will take this element. It is projected on this axis. So, no, not projected. It is rotating about this axis. So we have d3 times x1, because that's where the yield line is cut. So it's d3 times x1 divided by 2 times the maximum deflection, which is x1 divided by s1. So this term is for that piece of slab in this direction, and this term for this piece of slab in this direction. So now we put that for this corner too, and we have this formula. Now this formula is too large to be practical, so we'll cut up in different pieces. It does no matter how you do it. It's as long as you can use it. And we will calculate the work done by the internal forces. And this is the yield line here projected on this axis. The length is B, and the mean rotation is delta over S4. So that's this, delta over S4. Then we got on this side A over S3, on this side B over S2, and we have also this one, A over S3. Then we come to the yield lines. So we got this portion here projected on this axis equal to E minus this part. So B minus B4 minus B2, and projected on this axis is divided by S2, and projected on this side is 4. We divide by S4. And then we end up with those two little pieces. It's quite easy. This yield line is projected on this axis, so it is D4. No, not D4. It's X1. Sorry, it's X1 divided by S4. And for this piece, projected on this axis, it's D3 divided by S1. Just take care that according to this line divided by S1 and not by a lower value, because the whole flap has an angle of rotation delta over S. So the rotation angle is the same, even if it is shorter than this one or whatsoever. And we can fill in the different values, and we got an expression for dx. We know the bending moment is equal to this. Then we have the conditions of the horizontal position and the vertical position. Now let's see what we can do in practice. Suppose you have a concrete slab 200 millimeters thick, concrete covered 30 millimeters. The floor finish is 2 kilonewton per square meter, and the mobile load is 15 kilonewton per square meter. Now we are trying to calculate the needed reinforcement for this slab, and there is a reservation in the slab, for instance, for active cables or for ventilation shafts. What is the reinforcement? The maximum load in ultimate limit state is 1.35 times the permanent load plus 1.5 times the mobile load is 32 kilonewton per square meter. We write down the different parameters. We calculate S1, 2, 3, and 4, and the value Y1, X1, and X2. The horizontal position, we will check if we can use the formulas. We check the horizontal position, and we see that, okay, 4.8 is between those two limits. That's okay. Then D4 must be smaller than 2.89a, which is the case. And then the next condition is also okay. You have to check this to be sure that you have the right formulas. Vertical position, it gives us this condition, which is all right, and this condition, which is all right. Now, we will calculate the maximum bending moment, assuming, of course, that the reinforcement is equal to the bottom reinforcement. We calculate the in-between parameter h, and then we calculate the x, we calculate dx, and then from this on, you can calculate the bending moment, the maximum bending moment, which is 35 kilonewton meter per meter. We convert that in reinforcement. We assume diameter 10. We calculate the lever arm in X direction and in Y direction, and we take the mean lever arm, and it's 160 millimeter. The needed reinforcement is equal to the maximum bending moment divided by the um, lever arm and divided by the yield strength of the concrete, and we multiply by 1.1 because it's an upper bound method. We have 614 square millimeters per meter. This means diameter 10, 8 diameter 10 per meter, of 628 square millimeters per meter. And this is a reinforcement, bottom X direction and Y direction. So 4 times this. So when you reinforce a slab with a mesh of a diameter 10, 8 diameters per meter, then it will be fine. Second example, you have an existing slab. The only thing you know is that the bottom and top reinforcement are the same. And they ask you if it's okay to make a reservation 1.8 by 1.2 meters, to make a reservation like that, or for instance, electric cables. So we will calculate the maximum bending moment without the hole. This is M0 divided by Q, because Q we don't know, the load we don't know, so we put it there. What's left is only formula depending on the geometry. And so when we calculate this, it's 1.144. Now we can calculate the bending moment, the maximum bending moment with the hole. That's M over Q, or EX over DX, and gives you 1.145. So this means that the bearing capacity is equal, more or less equal to 100%. So there's no loss at all of bearing capacity. So yes, you can make a quite large hole or reservation in the slab without touching the bearing capacity of the slab. I'll give you now 2 examples of how you can use the methods and the different formulas in this video. For instance, we have a slab, 6 meters by 9 meters, and we want to make a reservation like this into the slab. And the length of the reservation is 6 meters, and the depth varies from 1 meter or 1.5 meter to something like that. Now I want to know the of the reservation, how does it affect the bearing capacity of the slab? We know that D3, it's from top up till there, that's D3, is in fact, because it's a central, it's the reservation in the center of the slab, we know then that D3 is 3 minus D1 over 2. And D1, the width of the varies from 0.6 meters to 4.8 meters. That means that D3 will also vary from 0.6 to 2.7 meters. So that's the limitation or the field of investigation for this type of reservation. So we can use dimensionless parameters. So we divide by A, and then you see alpha 1, which is D1 over A, is varying from 0.1 to 0.8. So the question is, what is the influence of this type of reservation on the bearing capacity? These are the different values of parameters, the range. Calculate S1, S2, Y1, Y2, and X1. And then we check for this type of reservation if the formulas are valid. The horizontal position, okay, that's a rounding off element, but it's valid. This is because the reservation is on the left edge of the support of the slab. We checked before, we checked this one, it's all okay. And then we check the vertical position. The vertical position is also okay. So it's fine, we can use the formulas in the previous slides. We can now fill in the different parameters for this case on the study. And here the maximum bending moment is only function of the width of the reservation. You can calculate the maximum bending moment without reservation, and from that we can calculate the bearing capacity, which is 100 times m0 divided by m, which is this formula. We can now make a graph. X-axis is alpha 1, going from 0.1 to 0.8, and the bearing capacity on the y-axis. And you see immediately that in most cases, the bearing capacity is not affected, not at all. Only here, with a small width of the reservation, we can have a problem. Let's investigate this more. The point which is of interest, where bearing capacity is 100%, then the alpha 1 is 0.137, or 0.137 times 6 gives you roughly 0.8 meters. So for every reservation bigger than 0.8, it's okay. When you go smaller than 0.8, it's not okay, which is rather counterintuitive. Now let's study the left corner of the previous graph, and we will now make a graph on the x-axis alpha 1, the y-axis the bearing capacity for alpha 1 up to 2, that's the total range, and alpha 1 is also here the total range. This is the two ranges, and you see that this is an interesting point. We enlarge this, and then you will see that in this area you lose bearing capacity. So you must avoid in this area to make a reservation that falls in this area. It means, for instance, if you make a reservation in a slab with b over a equals to 1.5, then we are here in the blue dotted line, then you could make a hole bigger than 0.12 times the smallest dimension of the slab, otherwise you will lose bearing capacity. So this is the total range, alpha going from 2 to 1, and then you see in this point here that the reservation of this type is okay for a width greater than 1/6 of the smallest dimension of the slab, which is here 1.66 or something like that. So that's how you can use the different formulas. It can learn you something about the best or worst position of a reservation in a slab. When we look at the formulation of BC, the bearing capacity, and we fill in for B1 equals 0. So in fact, it means that BC should be 100, because when alpha is 0, alpha 1 is 0, then there is no reservation made. But this is not the case. So you have this formula. So maybe something is wrong, because this is 100. Now we look it into detail, and from alpha between 1 and 2, the bearing capacity of slab without reservation follows this line. So it means that the smaller alpha, the less your bearing capacity is. So the smaller the reservation, the smaller the bearing capacity. That's alpha. That's here. Smaller the smaller the reservation is about D1. It is about alpha. So now, when D1 is 0, then in fact it implies that the yield line is cut. I'll give you an example. This is a very small reservation in the slab. So in limit, when this is getting to 0, I should reach 100%, which is not the case. So what happens when it's very, very small? Well, theoretically, this yield line is cut in the formulas automatically, and because this yield line is not visible in the formulas. So that's why Here we do not have 100% because it's like a very fine cut in the slab and the yield line does not work. So when D1 is now bigger than A over 6, then the reduction that you have here, because you have cut away this yield line, cutting away yield lines will say that you lose bearing capacity. So what will happen is that this surface, which is D1 times D2 times the load, it's a reduction in load. So as soon as you flip the reservation, what load was on the reservation is left away. So from a certain width of slab D1, this gets more important, and you do not lose total bearing capacity because there is no bearing capacity calculated where the reservation is. Now let's have a second example of a reservation in the slab going from this side to this side, and you want to know what is now the best position. What should be B2 length? What must be the length? Because A1 I fixed it on 0.1 times A and alpha 3, so it's in the middle. Let's look at this problem. Alpha 2 goes from 1 to 0.29. This to this. Now, what is the influence on the bearing capacity of this type of reservation? We know now the different parameters. We calculate the different variables. We look, we make sure that the formulas can be used. So we look at the horizontal position. So this means that alpha 2 must be between those two limits. B4 is smaller than this, that's okay. This is also okay. Vertical position, that's fine. And vertical position is fine. So what's left is here the horizontal position, because alpha 2 in this problem we are varying it, and alpha is also a variable. So this is the key limitation of our problem. We make a graph on the x-axis alpha 2. We know alpha 2. The limits are between a lower and an upper limit. So it depends on alpha. So let's look at alpha is 1.25, the blue curve. Let's look at that, the blue curve. Then you see this is the bearing capacity on the y-axis. It's this blue line. But after this point, when alpha is bigger than 0.75, the alpha 2 is getting out of range because alpha is here 1.25. So then the formula drops there. So this is only the validated or the range where the formula can be used. So each alpha has its own limitation, which is governed by this equation. So for instance, alpha is 1.5. Visualize it. This is the left border. And you see this is this point, alpha 1.5 is the black curve, is this point. And alpha is 0.209, 0.209 alpha 2, and BC is then, if you fill in the formula, 100%. So that's okay. Why is this 100% the bearing capacity? Because we have not got any yield line. Well, that's logic. Then on the right-hand side, the black curve here on the right-hand side, then alpha 2 is equal to 1 because alpha is 1.5 minus 0.5 gives you 1 at this point. So that's where it breaks off. And the bearing capacity is 96. And this is because we have cut the yield line. That's why. The difference between 100 and 96%, it's almost negligible. But anyway, it's about the principle. And then the last point there, right in the middle, you have for alpha 2.65, which is within this range, you have 98%. This is something nice to note. The red curve is always above 100%. So this means that this type of reservation does not lead to a loss in bearing capacity for square slab. Let's look at the region when alpha is not one, and when the slab is not a square. Let's look at what we have. This is a graph with on the x-axis alpha from 1 to 2, and we have plotted alpha 2. Alpha 2 max is where the bearing capacity gets its maximum value. And it's easy to calculate, it's just a little bit of arithmetic, and then that's the formula for alpha 2 max, which is the red curve. We know that alpha 2 has a limit. The lower limit is 0.289. That's the dotted line. That's the lower limit, 0.289. You have an upper limit, function of alpha minus 0.5. You see now on this curve, so this is the region that is valid between the black lines. This is the valid region. When you are in this region, for instance, alpha is 1 and alpha 2 is 0.4, you see that we have more than 100% bearing capacity. It means no loss of bearing capacity. When you have this point, for instance, alpha is 1.8 and alpha 2 is 1, then you have 95% of the bearing capacity, so you lose bearing capacity. Same for this point. So this means that in this area, you lose bearing capacity, you could avoid it. And in this area, you do not lose bearing capacity. So if you want to make a hole or a reservation of this type, you should work within this green region, or you should work in this green region.